Hello, this is Professor Kuehn, and welcome back to probably my last lecture for the semester on astronomy. We've been looking at Edwin Hubble's The Realm of the Nebula. And you might remember that what we've been talking about is what is now known as Hubble's Law. That is, that if you look out at the distant nebula, they all appear to be receding from us. That is, they seem to be moving away from us. And the speeds can be measured by looking at the light that is emitted from the nebula, specifically looking at certain spectral lines, the absorption lines. And we notice by looking at these absorption lines that they are redshifted. That is, they appear farther in the red end of the spectrum than they would appear if they were stationary. And you can deduce the velocities of these nebula from looking at the redshift of the spectral lines. So Hubble was able to discern that the most distant nebulae are the ones that are moving away from us most quickly, and the ones that are closest to us are moving away from us most slowly. This leaves to us a question of interpretation. Why are they moving away from us, and what does this imply about the past of the universe? And you can probably see where this is going. The Hubble experiment, or the Hubble law, basically leads us to the idea that at previous times, all of the nebulae were closer to us. And if you imagine that the universe was expanding at the same rate, that is, the nebulae were moving away from us at the same rate for all time in the past, that implies that at some distant time in the past, they were close to each other, in fact, infinitely close to each other, in fact, right on top of one another. And this is really the experimental evidence that supports the Big Bang theory as it has come to be known. Now, I just want to kind of talk a little bit about this because this is a point where philosophy and religion and science really intertwine with one another. And it's not the only place where they intertwine with one another. I think you've seen over the course of the semester in studying various topics in astronomy that there's not a clear line between science and religion and philosophy. So let's dwell for a few minutes on some of the challenges that Hubble's observations raise. So first of all, I want to point out that I know we didn't read any Isaac Newton this semester. I talked a little bit about Isaac Newton. In my Physics 151 and 201 class, we talk in more depth about Isaac Newton. One of the interesting things that he points out in his book, The Principia, is what are called his rules of reasoning. And one of his rules of reasoning is that it's called the principle of induction. This is not something that Newton came up with, but it's something that he emphasized. And the principle of induction, it goes something like this. Let me give an example. Maybe that would be the best way to explain it. So if I right now look out of my window and see a red bird sitting on the arborvitae tree right outside my window, I would say, oh, that's interesting. And then if I look out in 10 minutes or an hour and another day or another week, and every time I look out the window, I see a red bird, and that is the only kind of bird that I see, I might come to a general rule that all birds are red. That would be a reasonable kind of conclusion. It's based on induction. That is, from experimental evidence, I generalize to all cases based on particular instances. And one can develop laws of science based on induction. Of course, those are only as good as the particular observations that you make. So if Dr. Kuehn's law of induction that all birds are red only works insofar as all birds in fact are red. If at some point I look out and see a blue bird, that law would fall apart. So this is the idea of the principle of induction. And really the idea that Hubble presents at the end of this chapter is based on this principle of induction. It's sometimes now known as the principle of uniformity, or the principle of uniformity of nature. That is, our present observations of nature can be generalized and are held to be generally valid unless there's a convincing reason to reject them. So if, for example, he sees that all the galaxies are moving away from us at a certain speed, Hubble is invoking this principle of uniformity to say, therefore, it's a reasonable assumption to say they've always been moving at this same speed. And if you imagine kind of running the movie back in time, they should have been closer and closer and closer to us. And that implies that at some point in the past, they were all right on top of each other. And by looking at the speed they're moving at now, you can deduce that that would have been, according to Hubble, about 2,000 million years ago, or 2 billion years ago. The modern estimates, by the way, are more like 15 billion years ago, but that's neither here nor there. They're based on the same principle, the principle of uniformity. Now, of course, this prediction is really only as good as the assumptions that go into it. And there are reasonable assumptions. Don't get me wrong, I'm not criticizing the assumptions. I'm just recognizing as a point of fact that they're only as good as the assumptions that go into it. So one of the examples that I give, another example I give sometimes, is imagine that you are in your kitchen and you have a pot of water that's on the stove and the stove is on, and you decide to be very scientific and measure the temperature of the water in the stove. And you measure this every 10 minutes over the course of a few hours. And you find that when you measure the temperature of the water, it goes up by 10 degrees every minute. And you plot this in your lab book and you make a graph. There's a linear increase in the temperature as a function of time because you're being very scientific. And then you look at your plot over that you've collected data over the course of maybe 2 hours. And then you fit a line to your data and say, well, let's assume that this line, this linear increase in temperature, is a law of nature. Well, of course, the problems with that arise quite quickly if you try to extrapolate that back in time and say, well, if it's been increasing 10 degrees per minute for this 2 hours, if I go backwards in time by, let's say, 1 day, which is about 1,440 minutes, then that implies that the temperature of the water was negative 14,400 degrees 1 day ago. Of course, that would be an absurd conclusion because at some point somebody turned on the stove, right? So there was a non-uniformity that was not taken into account by my experimental observations. So this is just a point of fact that one needs to recognize when trying to generalize or extrapolate from observations right now into the past. And I think this is something that Hubble and other reasonable scientists are aware of. Another point that I'd like to bring up is a difficulty that Hubble himself also brings up, and this is that if we take Hubble's law seriously, that if the speed of the galaxies increases with distance, and if the universe goes on indefinitely in size, that implies that as you go to larger and larger distances, the speeds of the galaxies get larger and larger and larger, and eventually will approach the speed of light. And this is something that Hubble brings up as a puzzle or a problem. How is it possible that galaxies or nebulae can be moving at near the speed of light? Or in fact, if you extrapolate Hubble's law out to very large distances, the galaxy should be moving faster than the speed of light, which seems to be opposed to the law of the constancy of the speed of light, and light as being a universal speed limit that was fairly well accepted at the time of Hubble. Now, of course, the solution that modern cosmologists present to this is that the speed of light is a local speed limit. That is, it only applies to certain particular regions of space. And in a sense, the law of expansion of the space itself in which the nebulae are existing, the law of expansion of space itself is in some way exempt from this limitation imposed by the local speed of light. In any case, this is an interesting implication of Hubble's law that needed to be dealt with. Another thing I'd like to just point out here is that you can probably see how these cosmological or astronomical problems very quickly lead to both philosophical and theological problems, as I mentioned a few minutes ago. And one of the ones that I find most interesting is we did not get a chance to look at him this semester, but I'd like to just mention the work of George Lemaitre. He was a scientist in the 1930s. He was a Belgian scientist, astronomer, and he was a Catholic priest as well. And he, in the 1930s, is the one who came up with the idea, based largely on Hubble's law and the work of Albert Einstein. He came up with the idea that if you kind of run the movie back in time, as we talked about a moment ago, that you would arrive at a point where all matter, all galaxies were at a particular point. And he called this the primeval atom. And he imagined that all of the matter in the universe was concentrated at a specific point. And his opponents ridiculed his idea, saying that he had believed in this big bang, this big explosion that started the universe. And one of the things that's most interesting about this story is that at the time, in the 1910s, 20s, and before then, the idea was very popular that the universe was static. That is, that there was no beginning and no end to the universe. So if this sounds a little bit like Aristotle's theory of the universe, you're correct. Many of the astronomers at this time believed that the universe was infinite in size and it was past infinite. That is, it didn't have a beginning and it will not have an end. This was seen as a way to avoid kind of the question of creation. How did the universe come to be? After all, if it didn't have a beginning, you don't need to explain why it came or when it came to be or how it came to be. So when Lemaitre, this Catholic priest, came up with this idea that later became known as the Big Bang Theory, many of the astronomers saw his ideas as a way of sort of smuggling theology back into science, because after all, if the universe had a beginning, it must have a cause, and that cause has to be something outside of the universe. And so many of his opponents saw this Catholic priest as trying to smuggle theology back into astronomy. I find that interesting just because nowadays in many the Big Bang cosmology is seen as being anti-Christian, whereas when it was first established, or when it was first, conceived by Lemaitre, it was seen as a theological position. Now, whether or not you agree with Big Bang theory, that's beside the point. I think this is an interesting historical development of astronomy. I hope that this course has given you some very interesting things to think about, and I look forward to talking to you in the future.